Okay. Hey everyone, I am solving Advent of Code 2025 day 3 today. We have about 10 seconds to the actual start of it. Again, there is the template file that I created to handle solving the question. Okay, cool, let's solve it. So as per usual, I usually don't read the question first, I just paste the input and then deal with it later. So batteries are labeled from 1 to 9 and they are arranged into banks. Each line of a digit is a single bank of batteries. So you need to turn on exactly 2 such that it is equal to the number of digits formed by the digits of the bank you've right, so if I turn on 2 and 4, it produces 24 volts. So you need to find the largest possible voltage that each of them can produce. Okay. Basically, I think let's just parse it first. So for every line, as you can say, this is the banks. The banks can append for every battery in the line int of this battery, and we can just return these banks. So we should be expecting a list of integers. Let's just do the print again. Again, I have a CLI just to handle all of these operations. Oops. Part 1. Yeah, so you can kind of see we parsed it. Essentially what we want to do is we want to do some kind of greedy solution where we pick the largest first digit and the largest second digit where possible, and we can always guarantee that if we pick and there's a couple of corner cases. So one of the corner cases I can think of immediately is picking the largest digit at the very beginning doesn't always guarantee the largest number. Well, no. Yeah, because you could basically get a case which is really simple, which is something like 1 and 9, where the largest digit first is 9, but if you pick it, then the next digit you pick is 1, but because it comes in the wrong order, it won't work. So I think that's one of the main corner cases we have. So what we could do is we could literally brute force the solution. Maybe just looking at the inputs, it seems like possible that we can actually brute force it, where we literally just try all of the possible positions and just check what's the maximum. So we can literally just say for the bank in the data, so the n is the length of the bank in the range of n. So given a current digit I, let's suppose we pick some other number, which is everything after I. And so the answer, well, we can see here we are summing up the answer. So the answer is equals to 0. We can say that the result, or I guess we can say the max voltage is 0 for now. The max voltage is the max between the current max voltage, or if we take the bank at I multiplied by 10 plus the bank at j, and then afterwards we can just simply increase the answer by this. Yeah, you can kind of see here that's what we did. I am mostly brute forcing it right now because I think in the past few attempts I've always tried to over optimize it and it doesn't really work out all the time. So I think it's easier if I just try out the solutions and solve them first, and then afterwards explain a better solution and look for a more optimal solution. Okay, cool. So we've managed to solve part 1. Now let's look at part 2. Overcome the static friction. So of exactly 12 batteries within each bank, right? So we are picking 12 different batteries that can produce the largest voltage. So clearly now is where we actually need an optimization because we can no longer brute force it anymore. So I think the first way we can do is we can employ some form of greedy algorithm where um, where I think what we could do, well, yeah, so I guess like in here you would basically be saying, okay, let's pick two different points at any point and then see if that max voltage is equivalent or is sufficient, and then we will cruise it. Because we're picking 12, it's a lot more complicated. So I think, let me just close out this window. Let me try to think of what's a better solution for us here. I'm thinking if this is some sort of stack problem where the stack size is the maximum number of digits we are picking, and then it is a sort of a monotonically increasing stack where we push items onto the stack each time we see it. If we encounter a number that is larger than the previous number or the top of the stack, we pop the top of the stack and we push in the new item. And each and every time it is, so I guess it's a monotonically decreasing. So once we've encountered a larger digit, we would pop everything that is smaller, and then push the element, and then push my elements into it. And then as we do that, we can kind of do some matching. I'm not sure how this would translate into a more dynamic solution with 12 numbers. Because I guess in the very first example, it's very simple, right? We know that every number is decreasing, so we are always guaranteed to pick a much bigger number. We are always guaranteed to keep the numbers in the order. So we would push into the stack till the stack size is 12, and then for every other number, if it is not greater than the current top of the array, we kind of discard it. I'm trying to think if this is a viable solution, regardless, because what we yeah, so in my head, I guess it's kind of looking like for every number we encounter, we want to check, is this the largest we have seen so far? And if it's the largest we have seen so far, can I pair it with another number to make it better? Yeah. Let's see. Okay. Yeah, I'm kind of thinking this is a stack problem where we discard where we maintain a size of at least 2. So if it is not 2, we always push elements in as greedily as we can. And then if we have exceeded the size of 2, we decide whether or not we want to pop or whether or not we want to include it. Yeah. I guess maybe not just a stack, but it could be a double-ended queue, I'm thinking. Right, where like the yeah, I guess the fundamental I guess if we don't want to do this, we could literally solve this with DFS, where we have I, which is the position in the bank, and then the accumulated number, and then if I has exceeded the length of the current bank, I simply return the accumulation. And then each time we process this, let's say taken is an int. Each time we process this, we can say that if taken has already exceeded, if taken has already exceeded, I guess we say max taken, the max taken, we also return the accumulation, max taken, right? And then because basically we're saying that for every integer we either take it or we don't take it, and then we keep trying all of the positions, which is essentially the number of which is essentially kind of a subset-ish problem where we pick the numbers and then we either return the max of the DFS along the bank, where we take one and we increase this by one. We can say that it multiplies by 10 and then we include the bank of I, or the other alternative is it takes bank of I taken, or I don't take it, right? And then if the, well, I guess one thing we can also check is we need to make sure that if it is greater than n, it happens to be not less than it, we want to return 0 because there was no way it would have happened, right? And so now that we kind of have the function, we can say that for every bank in the data, we can say that the answer is increments by the bank. Let's just call this bank underscore, just so I don't have a name conflict. 0, there's none taken, the maximum taken is 12 along with an accumulation of 0, right? Yeah, so you can kind of see here, that's the fundamental logic. I'm pretty sure this might take a while for if we just solve it naively, because naturally this wouldn't really make sense. So what we could do is we could also provide a memo for this. So I think, let's say we let's say take, and maybe let's just generify this function, and let's just say this goes here, and let's just say that take, right? So I think this benefits a lot from having a memoized dictionary. So let's just say we have a memoized, it's a dictionary of a tuple of int and int, and then int again. The reason why I say it's a tuple of int and int is because the key is going to be I and the number of taken elements. So if key happens to be in memo, we return the memo of the given taken. So we can say here that the memo of the key is this value, and we can return this memo of this given key. Yeah, and it will say self take, and say self take, and let's just provide this the memo as well. Cool. Yeah, so I think there was quite a lot of extra branches, so that's the reason why we had to kind of do it this way. But let's just see if it works if we test it. No, it didn't. It is undercounting, it seems, which isn't necessarily what we want. So let me just think about it. I guess it's worth printing out the key first and then the memo, and I guess the accumulator. Right, so it is saying here that if the maybe let me just Okay, maybe let me just debug this on the previous solution here, where the size is actually 2, so that I have a much better control over how big this is. But yeah, so you can kind of see here that every time we enter the loop, we do produce numbers like 22. We don't really need the memo, so I just kind of want to see the key and the accumulator. Yeah, so you can kind of see here that it produces 88. 89 is one of the produced answers. I wonder if we need to account for the accumulator as well. Maybe. 357 and 321619. Yeah, so we did have to include the accumulation as well. Cool. So maybe this would be a bit faster. Probably not. But that is like one of the first ideas I have, which is to essentially try every position either takes or we don't take it, and then that is the answer. I am assuming that there is a greedy solution for this. So basically for here it is very slow because there is basically a very deep tree that can occur. And because of that, we are basically trying all the possibilities and probably failing at a lot of them. So let's just save this first and say solve day 3, 2025 with naive DP. So let me try to think of a more better solution for this. I think based on the constraints that we are seeing, we are very likely dealing with a problem that requires some kind of greedy solution, where we know for certain that picking those digits in a certain order is the kind of optimal choice for us to be making. And yeah, I am trying to think about what this could look like, right? So one way we could also solve this, or I guess one way we could also think of this, is by, okay, so I think one simple-ish way we can do this is we can iterate through from the very beginning and keep track of the maximum possible answer or maximum possible digit we can pick. Each time we find a digit that is larger than the previous, we ask the first question, which is there sufficient digits after this that can still form a number? And if there is, we would update that one digit to be the maximum. Otherwise, if there isn't any more digits, we know that we have already found the maximum we can have, and we kind of move on to the next digit. Yeah, I think that might be a much better solution as well, where let's suppose we say that we are, let's say, take batteries for a better name. So we have the bank, which is the list of integers, and we can say that the max taken is the integer. Integer, we can return -1 for this, and let's just do that. I think that kind of counteracts the case that I mentioned earlier, where if you have something like 1 and 9, we would have iterated through this, we have taken 1 as the max, and we have checked, okay, now if I'm at 9, can I still take 9, or is 9 not valid? And then that would have failed, right? So essentially the idea that I'm having here is we iterate from the start, when we encounter a number or a digit, so we track the largest digit seen so far. When we encounter a digit that is larger, we check if there are more values that can be taken to form max taken. If not, we reset the tracking and continue. Right? So essentially what we're doing is saying for I in range of the length of the bank, right? We can say the current largest or current max is always equals to 0 for now. And we can say if the bank of I is greater than the current max and the ith position, or I guess the n is the length of the bank, so let's just say n minus I plus 1 is still greater than max taken. So that means I have more digits I could take. So then you would say that the answer, or I guess the joltage, so this is a case where the digit can be taken, right? So we say that the current max is equals to the bank of I. Otherwise, if the bank of I is greater than the current max, right? I guess what we always want to do as well is we always want to pick the leftmost of this digit where possible, because that gives us the most amount of remaining space, right? So we always pick the leftmost largest digit in any consecutive group. Okay, let me just return 0 so it stops complaining about this. But yeah, so essentially if the bank of I, so let's suppose that I'm working on the case of something like 119, right? If I equals to 0, bank of I, which is 0, would be greater than, so 1 is greater than the current max, which is a 0. And the length of the number, which is 3 minus 0, so it is 3, it's this. So 3 minus 0 minus 1, essentially, would be 2, because there's 2 more digits. And so because it's greater, we can take it. And then we look at the other one, and then when this becomes a 1, we can still take it because the bank of I is greater than the current maximum. Is not greater than or equals to, it's equals to. So we skip it. Yeah, and so we can kind of track this as the left as well. Let's see if it's finished. It hasn't even finished, yeah. So I guess we could also keep track of the left, which tells me which digit I am currently which index I'm currently tracking. So I'm gonna say that L equals to the ith position, right? And the reason for doing that is because we want to be able to kind of backtrack. So essentially in this scenario here, we would have seen 1, we don't want to take it, we see 9, and we realize we cannot take it anymore. And then that's when we actually trigger starting to pick the next digit. So then we have to go back to the 1 again, which is the position we did not pick. So I guess this is more of a loop actually. So we can say that it is equals to 0, but we also have the right, which is also n minus, which is also happens to be 0. And instead of I, we say while r is less than n, right? Yeah, so the left becomes this right position. Right can increase as well. If there is a scenario where the bank of r is less than, but the current number is greater than the current max, and plus 1. So I guess the remaining digits is n minus r plus 1. So let's just write a variable for this. So we say the remaining digits. Remaining digits is less than the max taken. Oh, sorry. We need to keep track of the taken, which is the max taken. And then we say that the taken here so if there is not enough digits to spare, assuming we want to take it, so assuming we found a number that is greater, but we cannot take this because the remaining digits does not satisfy the number of takens that I require, I will say that now the right goes back to the left plus 1, right? And then we want to take this digit. We want to take what was previously stored as well. So we said that the joltage is equals to the joltage multiplied by 10 plus the current maximum. We set the current maximum back down to 0. And we say that L is equal to L equals to R. Because we chose not to take that digit. And we are now taking on the current maximum is actually the bank of 0. Yeah, something like this. I am not super sure if this works. It hasn't even completed yet. But maybe let's just say, let's try this out, right? So the max taken is 12 and everything else can stay. And let's just test this. If in all other scenarios it is either equivalent or not, we can always just increment the number by 1. Yeah. So that sort of overcounted really badly. So maybe let me just do this by solving for the simpler case first, which is 2 digits. Okay, so that produced a really large number, which is not what we expected. And that's because we did not reduce the taken by 1. So I've taken 1 digit, I should have stopped taking more digits. Okay, so we kind of see a more sensible answer here. I think one thing I'm starting to realize here is that the joltage, so it didn't pick the very last of this. So you can kind of see here, let me just increase the size again. You can kind of see here that in the first example, okay, let me see. Let's just run through this super simple example here. So we start with a position of 9, so that's the maximum taken. We realize that I see, because there could be a chance where I encounter such a large number that we can never pick it again. Let me see where it goes. Yeah, I wouldn't want to do it 12 times because it's basically n to the power of 12, which is a ridiculous runtime. especially if one row here is 100 digits. So it's 100 to the power of 12, which is ridiculously long. So I do not want to do that. So I'm thinking, yeah, I guess with this greedy solution in particular, it is always triggered by the fact of if I'm taking this digit and there is no other digit that can beat it, and then there is a chance that I go to the very end. I go to the very end and never have accumulated. Yeah. Yeah, and then because we've exceeded that limit already, yeah. Track the largest digit seen so far. So I am wondering if the DQ solution here makes the most sense in our scenario, where we always pick the positions that are, yeah, my suspicion here is that there is some sort of greedy algorithm that we are interested in. That can incentivize us to always pick the best digits. Yeah, and kind of from the look of it here, it does kind of seem like it's a stack where we keep track of the smaller monotonically decreasing stack. Kind of. But yeah, I'm not super familiar with it. Let's see, 889, 81, 81. I guess here there are sort of two other properties we have, which is we always want to optimize for the best digits at the front, and then the moment we hit a certain threshold, there is no choice but to take every other digit. Yeah, so I'm guessing that maybe this is what we are optimizing for, where we kind of make the argument that, okay, let's maintain some kind of stack at the very beginning. So as long as the next digit isn't greater than the current digit, we don't take it. But if I do encounter a point where I have taken some number of these digits already and I have nothing left, then I will fail. Yeah, that is kind of my suspicion, I guess. Although I am kind of doubtful that this could work. Okay, let me think. Yeah, because I'm assuming 100 choose 12. Yeah, it is a really large number of possibilities. Not particularly ideal to try them all. Yeah, I am not super sure how we could solve this. No. I guess maybe we could roll down the list of potential solutions, right? Off the bat of my head, there's like sorting, but sorting doesn't work because they don't allow you to rearrange the batteries. Um, there is possibly sorting, but we keep the indices of the sorted digits, and we always pick the top 2 or top 12 highest digits, and we just take whatever number that forms. That could also work, I guess. And maybe that's actually the much better solution here, where what we claim is we sort all of the digits by ascending order. We pick all of the digits that is available to us, and in some fashion, we always pick the digits that should appear as early as possible. And what I kind of mean by this is, let's suppose we sort the third example. We would get the highest digit being 8 and 7, and then 2 and 3 and 4 for everything else. But from this 2, 3 and 4 kind of list, what that could look like is then that could be, we would always take the largest digit and then just keep forming it until we get whatever number it generates. That could work, I guess. So maybe let's just delete this. I'm gonna delete this. Let me delete this as well. Where essentially the idea here is we sort with indices for the maximum across all. We just form whatever we can. I'm trying to think if there is a corner case where this might fail. And I'm pretty sure there could be one where essentially picking the highest possible digit at every position might not yield the highest possible number we want. Where, like, I'm trying to think in a case where we have 2 and 9 and 8 and 9, we would always pick 8 and 9. So maybe this is a possible solution as well. But this kind of calls for a heap. Oh, well, I guess we don't really need to. But essentially what we want to have is the bank with indices is equals to the enumerate for I in the range of the length of the bank. I kind of want to sort it by bank and I. So we say that the bank with indices sort, and we say that we reverse it. And I kind of want to just print the bank with these indices. Yeah, so you can kind of see here that oops, no. Yeah, oops, that was a mistake. Yeah, so we kind of see here, we pick 9 and 8 as being the two largest possible digits. And then everything else occurs. And then what we essentially want to do is we want to take the taken digits, which is the bank with indices, up until the max taken. So we know what are the digits we are choosing to take, which is 9 and 8, 9 and 8, 8 and 7, which again above this is 8 and 7, and then we get 8 and 6. Sorry, 8 and 2. Yeah, so I guess this is the corner case here, where picking the largest digit doesn't always guarantee that we could find the best possible answer. Where we could always find the best possible answer, because in this case we picked 8 and 9, but 89 is definitely less than 92. Okay, let me just pause it real quick so I can go and grab a notebook so I can write this down. Okay, so as it turns out, I kind of messed up. I did not enable recording, I just turned on the virtual camera instead. So there was like the last 20 minutes of me kind of actually getting the correct solution. But maybe let me just summarize what we did and look at what we can actually achieve. Okay, so essentially I listed out, I'll probably type this out and include it in the video, but I wrote down the solutions we tried, right? So there was the first solution where we basically brute forced all the possible positions. There was a n to the power of k solution where n is the size of the bank, k is the number of batteries we're choosing because we basically have to nest it. There is the dynamic programming solution where we basically, for every single digit, we either take it or we don't take it. And so this is sort of a two-level graph. A two-branch graph where we always keep branching. That didn't work because it takes way too long. There's too many branches for this. There was a potential solution where we tried sorting and greedily taking it, but I'm not sure if I captured the case here. But there is a potential where the largest digits happen to not also be in the correct positions, and so that creates a less optimal solution. There is the solution where we tried using a DQ. So I was kind of summarizing what I said, where we have where the variant we wanted, or I had in mind, was to have a DQ of the same size of k, where k is the size of the number of batteries chosen. And with a DQ, you normally think of the four operations we perform on it. We have when do we pop it, when do we pop the left, when do we pop the right, when do we push the left, when do we push the right. And we kind of came to the conclusion that it's not really feasible to use a DQ because within the DQ itself, there are digits you might want to drop in between, and there is no reliable way of figuring out what those digits are. So we actually went back to the initial idea that I had, where we naively take the leftmost largest within reason. And within reason is sort of a vague term, but within reason here is by essentially taking the largest possible number while having enough space for the rest. And the primary principle that we have here is basically math, or very basic math, where the leftmost digit influences how large the number is. So if I have a choice between 8 and a 9, I'm always going to pick a 9 if it's the leftmost digit. Because no matter what other numbers you pick, if you start with an 8, you're never going to become larger than the 9. So fundamentally, we want to always pick the leftmost largest number. And the way we can do this is we can keep iterating through the range of digits we have available and keep picking. So we keep going through them. We find what's the largest number that we can see within reason. We take it, we add it to the joltage, we count it as having taken one, and then we kind of shrink the range again, and we keep repeating this until we eventually take as many digits as we can. And so the way this manifests itself in the code, you can kind of see here, is we keep track of how many we have taken, which is, at first it starts with a 0. We keep track of the size of the bank, and there is the left and the right, which is essentially when we can start, the range in which we can start searching for the numbers, and the joltage. We keep repeating this algorithm while we haven't taken enough. We check that the remaining number of tokens or digits we have to take is the maximum number of digits we have to take minus whatever we have taken already, minus one additional one, because we're assuming we're going to take one as well. We keep track of the maximum that we have seen so far, which is the max of the bank on the leftmost digit and the digit itself, because we want to shrink the range eventually, so we need to know where the digit is. So essentially what we do is we say that we go through this entire range we have available to us, we see how many digits are remaining, so that is basically taken the n minus the current position of I, how many other digits are remaining. If the bank of I, so the current number that we're seeing, is greater than the maximum we have seen so far, not equals to, because equals to, we want to have the leftmost digit that is largest, and there is enough remaining digits to form for the subsequent algorithm to take some more. What we can do is we can set the maximum seen and the index. We then update the joltage, we then update the L, we then update the taken by 1 as well. And then we keep repeating this as long as we've taken it. And the wonderful thing here is this is an ONK algorithm, because it is the number of times you have to take, the number of batteries you have to take multiplied by the size of the bank every single time we iterate through it. I guess we didn't show it here, but you can kind of see here that the algorithm runs relatively quickly. I guess if we do a from datetime import datetime, and we do a start time, now timestamp, end, which is the datetime now timestamp, we can print the end minus the start. So we can print the number of milliseconds, the number of seconds it took, and we could print it as milliseconds. And you can kind of see here that it is blazing fast, because we are no longer relying on trying all possible digits. We greedily assume the property. So hopefully that was a clear explanation. This problem was very interesting. It took quite a lot of experimentation and figuring out what's the most optimal solution. And there were a few rabbit holes we went down on, but I think I'm pretty happy with the solution that we came up to today. Cool, thank you.